on the night of May 10th, 2026, a telescope quietly picked up something in the sky that nobody had ever seen before. A small, fast-moving point of light, drifting silently through the dark. Astronomers ran the numbers, and what they found made them sit up straight. This object, now officially named 2026 JH2, was already on its way toward Earth. And it was close. Really close. Just 8 days later, on May 18th, that asteroid came roaring past our planet at around 57,000 miles away. To put that in perspective, the Moon sits at about 238,000 miles. So this rock, somewhere between the size of a basketball court and a small office building, slipped past us at less than a quarter of the distance to the Moon, and we only spotted it 8 days in advance. Now here's what's keeping a lot of people up at night. 2026 JH2 didn't just leave for good. Its orbit loops back around, and when scientists started tracing where it could swing next, a few of those paths brought it uncomfortably close to Earth again, possibly before 2027 even arrives. So tonight, let's talk about exactly what this thing is and whether it could really hit us. To do that, we have to go back to the night of May 10th, 2026. Most of the country was asleep. Out in the desert just north of Tucson, Arizona, on top of a mountain called Mount Lemmon, a telescope was doing what it does every clear night, quietly sweeping the sky, snapping picture after picture, watching for anything that doesn't belong. This isn't some glamorous instrument hunting for distant galaxies. It's a workhorse. It's part of a survey program whose entire job is to scan the dark for things that move while the rest of us are at dinner, or watching television, or sleeping, and on that particular night, that telescope caught something. A single faint smudge of light, no brighter than a candle held up at the edge of the next state. The software ran its check. 2 pictures taken minutes apart, stars locked in place, smudge had shifted. Something close was moving. When you see something move that fast against the stars, your stomach drops a little, because distant objects don't shift like that. Distant stars don't shift at all on a time scale of minutes. Only objects inside our own solar system do, and the astronomers ran the orbit, and within a few hours they had their answer, and it wasn't the answer they were hoping for. This little smudge wasn't far away. It wasn't a comet drifting out near Jupiter. It wasn't a routine rock between Mars and the asteroid belt. It was already inside our neighborhood. It was already heading toward us, and it was getting closer by the hour. Now, you'd think with all our satellites, all our radar, all our space agencies and observatories, with all the money and intelligence we pour into watching the sky, something this big couldn't possibly sneak up on us. And the honest, slightly uncomfortable answer is, it just did. Until that night on Mount Lemmon, 2026 JH2 didn't exist as far as humanity was concerned. It had been drifting through space since long before our species learned to walk upright, and we picked it up exactly 8 days before its closest pass. 8 days. That's the warning we got. Less time than most folks take to plan a long weekend. 8 days between knowing nothing and watching it go by, so why didn't we see it sooner? It's a fair question, and the answer is the part of this story that I think most people don't fully understand yet. It comes down to 3 uncomfortable facts. The first is size. By the standards of asteroids, 2026 JH2 is small. The European Space Agency pinned it at somewhere between 14 and 30 meters across. So you're looking at a rock about the size of a school bus on the small end, or a basketball court on the large end. That sounds plenty big when you imagine it parked next to your house. But stretched across the gulf of space, it's a pebble. And small things reflect very little sunlight. They show up as faint smudges. Easy to lose in the noise of the sky. The second reason is color. Most asteroids are not the bright, shiny rocks you see in cartoons. They're dark, they're carbon-rich, charcoal-colored, and they soak up sunlight rather than bouncing it back at us. So even when one is fairly close, it can stay dim enough to slip past an automated survey unless the geometry is just right. But the third reason is the one that should bother you the most: the Sun. For most of the time before its discovery, 2026 JH2 was approaching Earth from a direction that put it almost on the same line as the Sun. And here is a truth that almost nobody outside of astronomy ever thinks about. Telescopes on the ground cannot look toward the Sun. The daytime sky is too bright, and at night, the Sun is, well, on the other side of the planet. So there is a vast cone of space, basically the entire region around our own star, where every ground-based telescope on Earth is essentially blind. Anything that approaches us from that direction has perfect cover. Picture yourself standing on a country road at sunset. You're squinting into the glare. Now imagine a black bird flies straight out of that sun, right at your face. You will not see it. Not until it is almost on top of you. That is exactly how 2026 JH2 made its approach. It came in from the sun's blind spot, and by the time it had drifted far enough to one side that a nighttime telescope could finally pick it up, it was already 8 days from its closest pass. And here is the quiet thought that I want you to sit with for a second, because the news cycle has already mostly moved on. There is no reason at all to believe 2026 JH2 was unique. The same blind spot is still there tonight. It will be there tomorrow night. And it will be there for every other rock that ever decides to come at us from that direction. Now let's talk about what this thing actually is, because I think the picture in most people's heads is wrong. When we say asteroid, people imagine a big grey potato spinning in space. That's not entirely wrong, but it doesn't tell you much. 2026 JH2 is a chunk of solid material, almost certainly a mix of rock and possibly metal, left over from the formation of our solar system about 4.5 billion years ago. It is older than Earth itself in a strange way, because the material that makes it up never got pulled into a planet. It's a leftover, a scrap that never made the cut. Astronomers classified it specifically as an Apollo-type asteroid. That's just a fancy way of saying its orbit around the Sun crosses Earth's orbit, like two racetracks that overlap. Most of the time, the two tracks have nothing to do with each other, but every so often the timing lines up and the two paths come very, very close. And the size is the part that really matters. 14 to 30 meters might not sound like much. So let me put it in a frame of reference that probably feels familiar. Back in February of 2013, in the morning sky over Chelyabinsk, Russia, an asteroid roughly 20 meters across came barreling into Earth's atmosphere. People were driving to work, kids were walking to school. Without any warning at all, the sky lit up brighter than the sun. A streak of fire tore overhead. A few seconds later, the shockwave hit. Windows shattered across 6 different cities. Around 1,500 people were injured, mostly from flying glass. The object that did all of that was about 20 meters across, smaller than 2026 JH2 might be. And nobody saw it coming either. So, when we talk about a 30-meter asteroid passing closer than the Moon, we are not talking about a planet killer. We are not talking about dinosaurs. We are talking about an object that, if it came in over the wrong city, could shatter every window for miles and hurt a great many people, and we got 8 days of notice. Now jump forward to the evening of May 18th, 2026, just over a week after that first faint smudge was flagged on Mount Lemmon. By then, telescopes around the world had been chasing this rock non-stop, pinning down the orbit hour by hour, and around 5:23 in the afternoon Eastern Time, just as most folks on the East Coast were getting home from work, 2026 JH2 made its closest approach to our planet. Here is the number, about 91,000 kilometers from Earth, at the moment of closest pass. In American units, that's roughly 57,000 miles. I want you to really sit with that, Because most people hear it and think, well, 57,000 miles, that's still pretty far. It isn't. Not in the language space speaks. The moon, that bright friendly face you've looked up at every summer evening of your life, sits at about 238,000 miles from Earth. So 2026 JH2 came in at less than a quarter of the distance to the moon. Less than a quarter. And here's the part that should stop you in your tracks. Your DirecTV satellite, the one beaming the Sunday football game into your living room, sits in geostationary orbit at about 22,000 miles above the equator. So 2026 JH2 passed Earth a distance only about 2.5 times farther out than that satellite. It actually flew between us and a chunk of our outer satellite network. If you imagine Earth as a basketball, the moon would be sitting 24 feet away across the room, and 2026 JH2 came in at about 6 feet from that basketball. 6 feet. In space, that is not a near miss. That is a flyby that should make every adult in the room go quiet. And it was moving. Relative to Earth, it was traveling at around 20,000 miles per hour. Fast enough to cross the entire United States in about 7 minutes. Fast enough that if you blinked at the wrong second through a telescope, you'd lose it. A handful of amateur astronomers around the world actually managed to catch it during the flyby. In their footage, it shows up as a tiny dash of light racing across the field of view and gone in a blink. There is something quietly haunting about watching that video. Because you are looking at a real, solid object, weighing thousands of tons, 4.5 billion years old, ripping past Earth closer than the moon, and we knew it existed for a little over a week. Now, the asteroid passed. It didn't hit. It didn't even come close enough for our atmosphere to pull on it or for our gravity to break it up. By the early morning of May 19th, it was already moving away from us, back into the dark. So in one sense, the immediate danger was over. But this is the part of the story that most of the news coverage didn't want to dwell on, and I think it's the part every adult watching this video deserves to hear plainly. If we missed something this close, this big, until 8 days before it arrived, what does that say about everything else that's still out there? The honest answer is hard to swallow. For asteroids in the size class of 2026 JH2, meaning roughly 20 to 50 meters across, astronomers estimate that we have currently catalogued maybe 1 or 2% of the total population. 1 or 2%. The rest, somewhere between 98 and 99 out of every 100, are still out there, drifting along their orbits, completely unknown, waiting to be spotted, if they ever get spotted at all. And that is not because astronomers are bad at their jobs. They're brilliant at their jobs. The sky is just enormous, the rocks are dim, and the sun's blind spot is huge. The really big ones, the kilometer-sized killers, those we've found. About 95% of those are catalogued, and none of them are heading our way anytime soon. That is the good news. The bad news is the small ones. The Chelyabinsk-class objects, the 2026 JH2 class objects, the city killers. Those are the ones that keep slipping through. So now the picture starts to come together, doesn't it? You have an asteroid, freshly discovered, just barely caught in time, swinging past Earth at a distance that would make any planetary scientist tighten their jaw. You have the uncomfortable truth that it was hiding in the sun's glare, and that there are tens of thousands of others just like it that we have never seen and may never see. And you have the question that has probably been sitting in the back of your mind since the start of this video. 2026 JH2 didn't just leave forever. It is not on its way to deep space, never to return. It's locked in a closed loop around the sun, a track that crosses Earth's orbit again and again, and the brief moment our gravity touched it on May 18th. That was not a clean handshake and goodbye. Earth pulled on that rock as it flew by. We bent its path just a little, not by much. but by enough that astronomers can no longer be perfectly certain where this thing will be the next time around. And the next time around might not be very far away at all. That is where the math gets interesting. That is where the calm, careful, almost surgical work of orbital mechanics meets the very human fear of looking up at the sky and wondering what is coming. Because the same gravity that just wrapped its fingers around 2026 JH2 and let it go could be setting that rock up for a return visit. A second pass. And when astronomers started running the projections forward, looking at where this thing could be over the months ahead, a handful of those projected paths came back with something nobody really wanted to see. Tracks that bring 2026 JH2 uncomfortably close to Earth again, possibly before 2027 even arrives. So the real question isn't whether we got lucky on May 18th. We did. The real question is whether we'll get lucky the next time. And to answer that, we have to walk into the strange, beautiful, slightly terrifying world of how astronomers actually figure out where a rock in space is going to be. Because in that world, a single tug from Earth's gravity, a whisper of sunlight, even a tiny invisible region in space the size of a football stadium, can be the difference between a peaceful flyby and a very bad day. That world isn't science fiction. It's the world we live in right now, every single day, whether anyone tells us about it or not. And to walk into that world properly, we have to start where every asteroid story really begins, the orbit. Because every question about whether a rock from space can hit Earth, every calculation, every prediction, every late-night argument between two astronomers staring at a screen starts with one fundamental fact. The asteroid isn't drifting, it's falling. It has been falling for 4.5 billion years, locked in a long looping path around the Sun, on a track that obeys the same calm ancient mathematics that holds the planets in place. 2026 JH2 is what astronomers call an Apollo-class asteroid. Just a fancy way of saying its orbit crosses Earth's orbit. Picture two racetracks built around the same Sun. One is ours, nearly circular, the way a horse runs the inside rail. The other belongs to 2026 JH2. Longer, more stretched, slightly tilted, swinging out past Mars and back in again. Most of the time, those two tracks have nothing to do with each other. Earth is on one side of the solar system, the asteroid is on the other, and nobody on Earth ever even knows it exists. But every so often, the timing lines up. The asteroid comes swinging into the inner solar system at the exact moment Earth is rounding the corner, and the two paths come close. That, in cosmic terms, is what happened on May 18th. The geometry was right. The timing was right. And we found out about it 8 days before it arrived. So the obvious next question, the one I know is sitting in your head, is the one this whole video has been building toward. Now that we know this rock is on a closed loop, now that we know its track crosses ours, when does it come back, and could it hit us before 2027? Let's answer it honestly. Not the way a clickbait headline answers it, the way the actual math answers it. Astronomers around the world spent the days during and after the flyby pinning down 2026 JH2's orbit with surgical precision. Every observation tightens the calculation. The way it works is almost beautiful. You start with a few points of data where the asteroid was at a few specific moments, and you let the laws of gravity do the rest. The Sun pulls, the planets pull, just a little. Even Earth, even the Moon, leave their fingerprints on the path. You add it all up, you let the equations run forward, and a path emerges. Not a perfect path. Never a perfect path. There's always a small cloud of uncertainty around it, an envelope of possibilities that astronomers call an error ellipse. But as the days go by and more data comes in, that envelope shrinks. The cloud narrows, the future sharpens, and here is what the math says about 2026 JH2 itself. This is not my opinion. This is the verdict from NASA's Center for Near-Earth Object Studies, from the European Space Agency, from every observatory that tracked this thing. 2026 JH2 will not come back close to Earth again until the year 2060. And when it does come back, in the year 2060, it will be approximately 17 times farther from us than the Moon. Not closer, not even comparable, 17 times farther. The probability of it striking Earth before 2027 is, for all practical purposes, 0. The probability of it striking us in 2060 is also 0. On the official Torino scale, the system astronomers use to rank impact threats from 0 to 10, 2026 JH2 sits at 0. There is no asterisk, there is no but. This particular rock, this specific Apollo-class asteroid that just gave us the scare of the decade, is not coming back to finish the job. And if you let out a breath right there, I don't blame you. That's the honest answer. The video could end on that note. Roll credits. Go to bed. But you would be missing the part of this story that I think actually matters more. Because here's the thing about 2026 JH2. It was never special. It wasn't sent. It wasn't aimed. It was just one rock out of a population that astronomers estimate runs into the tens of thousands. 2026 JH2 was a sample, a demonstration, a test of how our planetary defense system actually performs in the real world. And the test came back with a result that should make any thinking adult sit up a little straighter. We saw it 8 days out. 8 days, and it was perfectly safe. So now flip that around. If the very next 30-meter rock that comes at us is on a path that does intersect Earth instead of just sliding past, we will have, on average, the same 8 days of warning. Maybe less, and there is no rule, no law of physics, no celestial guardian that says the next one has to miss. This is where the story turns from one asteroid into the bigger picture. And the bigger picture has a few names that every adult should at least vaguely know. The first is the gravitational keyhole. It sounds like science fiction, but it's real, and it is one of the most quietly terrifying ideas in modern astronomy. Here's how it works. When an asteroid passes near Earth, our gravity tugs on it. The path bends, not by much but a little. The exact amount of bending depends on exactly where the asteroid passes. Astronomers have calculated that there are tiny invisible regions of space, sometimes only a few hundred meters wide, where if an asteroid happens to pass through during one flyby, Earth's gravity will tug it onto a perfect path for a collision on the next orbit. Years later, decades later, through one of these little regions, gravity does the aiming for us. The most famous example is an asteroid called Apophis, which made headlines years ago because there was a small chance it would pass through a keyhole during its 2029 flyby and come back to hit Earth in 2036. We tracked it more carefully and ruled it out. It's safe, but the keyhole was real. The math was real. And there are keyholes scattered all through near-Earth space, attached to thousands of orbits we haven't even found yet. There's another effect you should know about. It's called the Yarkovsky effect, and it's the gentlest, slowest, most patient force in the solar system. Sunlight hits one side of an asteroid, warming it up. As the rock spins, the warm side rotates into the dark, and the heat radiates back into space. And every photon of that escaping heat carries a tiny push, a microscopic thrust. So small you'd never notice it on any reasonable timescale. But over decades, over centuries, a 30-meter rock can drift hundreds of kilometers from where you'd expect it to be. The Yarkovsky effect is sunlight, very slowly rearranging the solar system. It is one of the reasons astronomers can't just calculate an asteroid's path once and walk away. The rock keeps quietly thrusting. And the longer the prediction window, the more uncertain things become. So now lay it all out. We have a population of tens of thousands of city-killer-sized asteroids in our neighborhood. We have catalogued maybe 1 or 2% of them. We have a giant blind spot facing the sun. We have gravitational keyholes scattered through the geometry of space, any one of which could hand-deliver a future collision. and we have sunlight quietly nudging the orbits we do know about. Now ask yourself the real question, the one this whole video has been driving toward. Could an asteroid hit Earth before 2027? Not 2026 JH2 specifically, we answered that, but could something hit us before the year is out? The honest answer is, statistically, the probability is small, but it is not zero. Astronomers estimate that a Chelyabinsk-class object around 20 meters hits Earth on average somewhere between once a century and once every few decades, depending on whose model you trust. A Tunguska-class object around 50 meters hits roughly once every several hundred years. Those numbers don't mean we're due. They don't mean we're not due. They just mean the door is always slightly cracked open, and if one did come, here's what you'd be looking at. Picture the morning of June 30th, 1908. A remote part of Siberia called Tunguska. Reindeer herders looking up at a clear summer sky, and then, with no warning, the sky cracks open. A streak of fire brighter than the sun. A shockwave that knocks people off their feet from hundreds of miles away. By the time anyone walks into the impact zone weeks later, they find an area roughly the size of metropolitan Houston completely flattened. 80 million trees snapped at the trunk and laid down in a pattern radiating out from a single point in the sky. There was no crater. The object never even touched the ground. It had exploded high in the atmosphere with the force of a large hydrogen bomb. That object was probably around 50 to 60 meters across. Larger than 2026 JH2 at its biggest estimate, but in the same general class. If a Tunguska-class event happened today, over a major American city, the death toll would be measured in the millions. This is not paranoia, this is documented physics. This is what we know happens because it has happened. The good news, and there is good news here, is that we are not the same species we were in 1908. We are not even the same species we were in 2013, when Chelyabinsk caught the world flat-footed. In September of 2022, NASA did something that, when you stop and think about it, sounds almost made up. They launched a spacecraft called DART, the Double Asteroid Redirection Test. They aimed it at a small asteroid called Dimorphos, about 7 million miles from Earth, and they slammed into it. On purpose. At over 14,000 miles per hour, and it worked. The impact changed the asteroid's orbital period by about 32 minutes. For the first time in the history of life on Earth, a creature on this planet reached out and moved a chunk of the solar system. We have right now working technology to push an asteroid aside. The catch is, it only works if we see the rock far enough in advance. Years, ideally. Not 8 days. That is why the story of 2026 JH2 is really the story of what we do next. NASA has a space telescope on the way called NEO-Surveyor, designed specifically to look in infrared light from a position near the sun, finally giving us eyes inside the blind spot that 2026 JH2 used to sneak up on us. The Vera Rubin Observatory in Chile has just begun its decade-long survey, and over the coming years, it is expected to discover more near-Earth asteroids than every previous survey in history combined. Within a decade, the catalogue will look very different. The dark places will get smaller. The 8-day warning will become months, maybe years. We will not be done. We will never be done. The sky is too big and the rocks are too many. But the silent sneak attack, the species-ending surprise, gets harder every year. So when you ask the question that started this video, could 2026 JH2 hit Earth before 2027? The answer is a clean and clear no. That specific rock is gone, drifting back out into the dark, not due to come anywhere close to us until the year 2060, and even then at a perfectly safe distance. But the question underneath the question is still wide open. Could one of its cousins, one of the tens of thousands we have not found yet, swing in from the sun's blind spot before the year is out? The math says it is unlikely. The math also says it is not impossible. And the strange, humbling truth is that we have more eyes on the sky tonight than at any other moment in human history, and even that may not be enough. Somewhere out there, right now, while you are watching this video, automated telescopes are scanning the dark. Astronomers are sipping cold coffee at their desks. And the next 2026 JH2 is already on its way. We just don't know its name yet. That is the part that should stay with you, not the rock that just passed, the rock we haven't seen.